Welcome to this explainer. Today, we're going to dive into a conceptual journey that is, honestly, going to completely shatter your everyday assumptions about how the physical universe actually works. You know, we interact with physical forces all day long, without really giving them a second thought. But right now, we are going to look at two seemingly completely different phenomena and reveal how they are secretly the exact same thing.
So let's just jump right in, okay? At first glance, electricity and magnetism seem totally separate, right? Think about it. Getting a random static shock from rubbing your socks on the living room carpet feels absolutely nothing like a magnet snapping up a paperclip from your desk. They just don't seem related. I mean, if they were, why aren't the batteries sitting inside your TV remote sticking to your refrigerator door? They just behave entirely differently in our day-to-day lives. And hey, if you've always thought they were totally different forces, you're in really good company. For thousands of years, dating all the way back to the philosopher Thales of Miletus in ancient Greece, humanity operated under this exact illusion. Thales noticed that magnetic lodestone could attract iron, and that rubbing amber could make it attract little feathers. But he categorized them as two completely unrelated, entirely different forces. And you know what? For centuries and centuries, that was just accepted as hard scientific fact.
But then, the 19th century hits. And boom, everything changes. A rapid-fire succession of total accidental discoveries, brilliant physical experiments, and some truly next-level mathematics began building this entirely unexpected bridge between these two forces. In what was really a blink of an eye, historically speaking, the brilliant minds of Ørsted, Faraday, and Maxwell completely rewrote our understanding of reality itself. So let's look at exactly how this incredible story unfolded.
Okay, so the very first major clue, it actually happened by total accident in 1820, when Professor Hans Christian Ørsted realized that a moving electric current generates a magnetic field. But what makes this story so wild is that it happened right in the middle of a live lecture at the University of Copenhagen. He had just happened to leave a standard magnetic compass sitting next to a conducting wire. When he ran an electric current through that wire for a demonstration, the compass needle suddenly deflected. He realized right then and there that an electric current flowing through a wire produces a magnetic field in circles right around it. This is, very likely, the only major physics discovery ever made in front of a live studio audience.
Now, take a look at these original notes from Michael Faraday. Following up on Ørsted's crazy live discovery, Faraday set out to see if the reverse could be true. Basically, if electricity could create magnetism, could a magnet create electricity? Well, through some absolutely brilliant physical experiments, he proved it definitely could. He figured out that just placing a stationary magnet near a wire loop did absolutely nothing. But, and this is the kicker, if he rapidly moved a bar magnet into or out of a coil of wire, it induced a transient electric current. He proved beyond a doubt that a changing magnetic field actually induces an electric field. This is a process we now call electromagnetic induction.
Section 1. The mathematical elegance and James Clerk Maxwell's enduring legacy. So, all of these very tactile, hands-on discoveries from Ørsted and Faraday perfectly set the stage for a Scottish physicist named James Clerk Maxwell in the 1860s. Maxwell took all these messy physical experiments, the wires, the compasses, the moving magnets, and he translated them into four incredibly elegant mathematical equations that literally governed all of electromagnetism.
What Maxwell found in the math was just beautiful. It revealed this perfect, self-regenerating cycle. He realized that if you could create an oscillating magnetic field in empty space, it would automatically produce an oscillating electric field. And then, well, that oscillating electric field would turn right around and produce a magnetic field. And on in this endless, infinite loop. The electric and magnetic fields basically oscillate at right angles to each other, constantly dynamically regenerating one another as they travel through empty space. And the craziest part? They don't even need any charges, magnets, or masses around to keep the whole cycle going. His equations boldly predicted that anytime you have an electric charge that accelerates, it sheds these invisible waves of energy out into the universe. The best way to picture it? It's exactly like a speedboat cutting across a calm lake. That boat leaves a sprawling wake of water waves behind it, right? Well, accelerating electrons leave a wake of electromagnetic waves behind them in the exact same way.
But right here, this is where it gets truly mind-blowing. Maxwell decided to calculate the speed at which this endless leapfrog cycle of electric and magnetic fields would travel. To do this, he just plugged in some basic, already known electric and magnetic constants, and his math spat out a jaw-dropping number. roughly 2.99 times 10 to the 8th meters per second. Now, that wasn't just some random number. That was the exact already measured speed of light.
Which meant one absolutely massive thing. It proved that light itself is simply an electromagnetic wave. It's just a coupled, propagating oscillation of electric and magnetic fields. By proving this, Maxwell successfully tied optics, electricity, and magnetism together into one single unified framework. Think about that for a second. The radio waves carrying your music, the microwaves heating up your leftovers, the visible light we see with our own eyes, and the x-rays at the doctor's office, they are all exactly the same physical phenomenon. Literally the same thing. They're just electric and magnetic fields dancing together at different frequencies.
Section 2, the relativistic twist, and solving the fishy behavior of moving charges. Now, Maxwell's equations were an absolute triumph of science. But by the late 19th century, physicists were scratching their heads because there was still a deeply fishy paradox about moving charges that Maxwell's classical perspective just couldn't quite explain. It actually required Albert Einstein's theory of special relativity to come along and finally solve the puzzle.
So let's walk through a little thought experiment to really understand this paradox. I want you to imagine an infinitely long wire with an electric current flowing right through it. Now imagine a single electric charge moving continuously upwards, running parallel right next to that wire. Observer B, who is standing stationary on the ground, sees a moving charge next to a current-carrying wire. According to standard physics, the current creates a magnetic field, and that magnetic field pulls the moving charge toward the wire. Simple enough. But now, imagine observer A. They are riding upwards in a glass elevator at the exact same speed as our floating charge. To observer A in the elevator, that charge isn't moving at all. To them, it's completely stationary.
And boom, here is our paradox. It's a fundamental rule that stationary charges do not feel magnetic forces, period. So how on earth can observer A in the elevator explain the charge still being pulled toward the wire? Because both observers absolutely must see the charge physically move toward the wire. You can't just have two entirely different physical realities happening at once. So without totally breaking the fundamental laws of physics, how exactly does the passenger in the elevator explain this attractive force?
Well, Einstein's special relativity steps in and provides a totally mind-bending answer. Because the elevator passenger is moving relative to the positive charges inside that wire, relativity tells us those moving charges undergo something called Lorentz contraction. Basically, the physical space between the positive charges literally squishes together from the perspective of the person in the moving elevator. And because they are squished closer together, the actual charge density changes. So the wire, which is perfectly electrically neutral to the person standing on the ground, literally appears electrically charged to the moving observer.
Which brings us to the ultimate breakthrough here, a mathematical object called the electromagnetic tensor. You see, what the person on the ground calls a magnetic force pulling the charge, the person in the elevator calls an electrostatic force pulling the charge. The physical end result is exactly the same, but the mechanism behind it changes it based entirely on the observer's frame of reference. Under Lorentz transformations, electric and magnetic fields literally, physically transform into one another. They are completely interchangeable depending purely on how fast you happen to be moving.
So, here is the huge ultimate payoff of all this. The fundamental force of magnetism isn't actually a separate force at all. No way. It is quite literally just two sides of the same coin, electricity plus special relativity. If you start with a pure electric field in one frame of reference, simply looking at it from a moving frame of reference gives you a magnetic field. Magnetism is, at its core, just electricity viewed from a different perspective. They are perfectly unified as electromagnetism.
Which really leaves us with one massive final thought for this explainer. Think about it. Humanity spent thousands of years absolutely convinced that static shocks and magnetic lodestones were totally unrelated things, only to discover they are the exact same force just wearing different masks. So if these two entirely different-looking forces are truly one unified thing, well, it really makes you wonder, what other seemingly separate parts of our reality are secretly exactly the same thing, just waiting for the right perspective to finally unite them?